Yeah, so there is an issue. The camera will try to follow you. So if you talk here, the camera will come. So you don't need to be concerned about this.
Yeah, but when I look and
You're gonna see yourself. There's no way to avoid this. Maybe there is. O Roberto não tem? Let me ask. Tem algum jeito de ela não ver essa foto? Uma gente minimizar? Como é que
I
faz?
think me presenting. It's 100% I do not want to do. Yeah, like, cause then all I'm gonna do is look at that and I'm not gonna. For the slides. Thank you. Nobody wants that. You, no, you can, but you don't want to look at, watch yourself give this presentation,
So,
right? Like on Zoom, you can't, like your hair, all you can pick about is with your hair.
I just work on the face of my face.
Yeah. Or they can see you rolling your eyes when, you know, somebody says something stupid, and they're like, oh, my God.
just a second.
Yeah, no problem.
One more
One more thing.
thing. So
It's fine.
today is crazy. There's the accident.
Yeah, I could, at least you called us good time. Early. Yeah, like. Right?
Wait, we almost set up.
Okay. Yeah.
And then just introduce yourself.
Yeah. I think it's air.
Yes. Okay, guys, so let us start this seminar. This is part of our graduate seminars series. It's our great pleasure to introduce Dr. Sallie Greenberg. She's a strategic energy advisor with more than 30 years of experience in carbon management. Dr. Green specializes and consults in many areas, including strategic energy project development, government relations, energy policy, health and environmental and social justice, team effectiveness, and energy leadership development. Dr. Green brings together a unique combination of technical one-of-a-kind project and programmatic experience, social community engagement, and policy-related expertise, with an emphasis in health and environmental considerations. As a former principal research scientist at the Illinois State Geological Survey, University of Illinois, Dr. Greenberg led the Illinois Basin Decatur project, a 1 million ton PE CCS project, to completion and has consulted and contributed to more than 30 energy and CCS projects, especially in project development, risk reduction, and stakeholder engagement. She led the Midwest Geological Sequestration Consortium and the regional U.S. Department of Energy Regional Partnership, and co-led the Midwest Regional Carbon Initiative Partnership. Dr. Greenberg holds a PhD in secondary and continuing education and Master of Science degree in Geology from the University of Illinois, and a Bachelor of Arts degree in Geology from Alfred University in New York. So it's a great pleasure to have her here. She's been in Brazil for a week. This time she went to Rio de Janeiro. Now she and Alan is also with us. She's from ExxonMobil. She actually introduced me to Sallie. I'm very grateful to this. And Sallie is also going to work with us and learn an extension course that is going to be promoted in our university in CCS. So we also had the opportunity to talk to her about this model. So Sallie, thank you so much for this. It's extremely pleasure to have you here. And please, the floor is yours.
Thank you. Can everybody hear me okay?
Yes.
Good. No need for a microphone, the way I prefer. Today we're going to talk a lot about carbon capture and storage. But before we do that, I want to set the context, if you will. As I think you are all aware, there have been many recent and continuingly increasing weather, climate related disasters, and we are seeing an increase in the frequency and in the intensity related to the emission of greenhouse gases into the atmosphere. These are just some of the events that have touched Brazil in recent years. So when you look at Brazil from an emissions standpoint, you're actually the 6th largest emitter in the world, behind China, Russia, the EU, India, and the United States. And so a significant amount of potential for reducing the amount of emissions exists within Brazil, which has the opportunity to make a large contribution to the overall global environment. About 1/3 of that emissions profile, which is quite unique to Brazil, is related to deforestation and land use. But the other 2/3 are primarily from agriculture and from energy production. And so these 2/3 really represent your best opportunity, if you will, for reducing the amount of overall emissions being put into the atmosphere. There's a lot of conversation and a lot of political milestones or goals related to 2030, 2035, 2050, with the idea that we can achieve net zero emissions. Countries sign on, you are hosting the COP in a couple of months. But when you think about today or tomorrow is October 1. So we are almost at the end of 2025, and 2030 is really only 4 years and a few months away. So very quickly, these milestones are coming up for us, and there is a lot of work that still needs to be done in this period. There's a few organizations, global organizations. The Oil and Gas Climate Initiative is one, very interested in the possibility for carbon capture and storage, carbon utilization in Brazil. And so you are starting to see the development of industry and regulations, all of the things that you need to have in place in order to be able to create a system in which you can capture, transport, and store carbon dioxide. I'm going to talk a little bit about, I'm going to go back and forth a little bit between Brazil and the United States, because in the United States, we have been working on these issues for about the last 25 or 30 years. And so there's a great opportunity for Brazil to learn from the United States, to learn from Australia, to learn from the United Kingdom, from the EU, from work and projects that have already been done. So in other words, you don't have to start at the very beginning. You can kind of start in the middle of the learning curve and the development curve. So in the United States, we had a federally funded program that has been in place since 2003 that looked at different regions in the United States to understand the possibility for carbon capture and storage unique to those specific regions and tied specifically to the geology. Because geology, as a geologist, I feel it's okay to say, is one of the most important components that is unique and isn't always available in every location, suitable geology. So these slides, just a variety of federally funded programs that have moved us up the learning curve. So in the United States, we started very much in the research space with looking at small pilot studies, maybe 10,000 tons, moving up to 100,000 tons to 1,000,000 tons, and then looking at locations where you could take carbon dioxide from multiple sources and store up to 50 million tons, for example. That's not being done, but the geologic characterization is being done. So where could you do those things? So in thinking about Brazil and Decatur, which is a city in Illinois, which is the state where Chicago is, where the big lakes are. So, but it's kind of in the middle of that state. There are a lot of similarities between where Brazil is now and where we were 25 years ago in Illinois or in Decatur. So and I'll go through these. So they're a little bit out of order, but I'll go through them anyway. So bioenergy, CCS, which is carbon capture and storage from the production of biofuels or from the production or using biomass to generate electricity. So in Brazil, you're using sugarcane to create ethanol. In the United States, we're using corn to create ethanol. This is the easiest, fastest, cheapest way to have a pure source of carbon dioxide, which is easily manageable for carbon capture and storage. So sometimes we say it is the low-hanging fruit because it is easy. When you are taking carbon dioxide from, say, a stack at a power plant, that is only maybe 10 or 12% carbon dioxide. A lot of it is water vapor, some of it is sulfur compounds, nitrogen compounds, other things in the stream. So the more pure your CO2 stream, the easier the capture is. You also have a situation where you have a lot of oil and gas knowledge and technology that can be applied to understanding the subsurface, to knowing how to do the engineering on the surface, how to build pipelines. But you also have locations where you may be storing carbon dioxide using geology that are not old oil and gas fields or mature oil and gas fields, but in fact have no hydrocarbons associated with them. And that creates a situation that is a lot like exploration as opposed to established industry. You also have, you may have, especially in the locations I was just talking about, people in the public who are not familiar or recognize oil and gas activities. So that not being familiar means people maybe have more concerns, a little bit more, many more questions, may not be as open to accepting or understanding the ideas of new technology. Here you have a set of regulations that are just in the stages of being developed. In the United States, when we started doing the project that I'm going to talk a lot about, we had an existing set of regulations, but they had not been tested. So they existed, but the project I'm going to talk about, first project to get those permits, which is not always easy. You have also here the possibility for storage onshore or storage offshore. This is also true in the United States. Yeah, so as you can see, a lot of commonality, a lot of similarities. In Illinois, this is sort of the learning curve I was talking about. So we started with a 1 million ton carbon capture and storage project moved to a 4 million ton project or a project that stores 1 million tons per year. First project was about 360,000 tons per year. So you can see you're scaling up. Then we have the situation where I mentioned previously, where you are characterizing the geology to understand where you could store 50 million tons over 20 years or 30 years. And then you have joint projects which are industry and the government, so public and private funding. And then ultimately, you are starting to see in the United States completely commercial, industry-led projects without government support. So we had to do this whole thing. It took 25 years. What I would imagine is that Brazil can actually start somewhere in the middle of that. So accelerating a lot of time. The other thing that building of different projects, stringing them together does for us is that we have experience in the entire project process, from screening to understand where you can do carbon capture and storage, to pre-feasibility studies, to feasibility studies and financial investment decisions, executing and constructing regular operations, and then site closure. So we understand every part of the process in a somewhat condensed format. The bottom line, the punchline of this presentation is that we know from the work that I'm talking about today that you can store carbon dioxide deep in rocks 2,000 meters beneath the surface safely, effectively, and responsibly. And you need all different pieces. It's not just technology or science or engineering, but you need policies, government policies. You need social interaction with people who live nearby or work in the companies. And you need this set of regulations by which you are ensuring the safety and the responsibility for people and the environment. One last thing along the bottom, you'll notice that these words are sort of a timeline. Barriers, obstacles, challenges, success, deployment, impacts, evolution. So I put those words there because I've been doing this a very long time, probably since before some of you were born. And what I have noticed is the way we talk about the effort or the way in which we approach the challenges associated with developing a new industry or doing the research and deploying it has changed over time. We used to talk about the very beginning, technical and non-technical barriers. So to me, if I'm at a presentation and somebody says, we're going to talk about the technical and non-technical barriers, it's like a clock in my head. And I'm like, oh, they're new. They're new to this space because they're using language that many of us have moved beyond, right? And so once you start to address the obstacles and the challenges, each one is a new step forward. So this is a relatively simple view of the challenge ahead of you, whereas each step gets more and more complicated, but more and more fruitful or beneficial, right? You make progress, what I'm trying to say. So at its very basic configuration, carbon capture and storage is the capturing of carbon dioxide, typically from what we would call a point source or a large source of emissions. I emitting carbon dioxide, but I am not a very efficient place to capture carbon dioxide. Whereas a power plant or an ethanol plant or something where you have a large volume of carbon dioxide is much more efficient. You can also use a process called direct air capture, which essentially vacuums carbon dioxide from the atmosphere. The difference in volume between direct air capture, which can typically capture about 1,000 tons per year, or 4,000 tons per year, depending. And the project that I'm going to talk to you about, which is a relatively small project, is 1,000 tons per day. So you can see scale-wise, direct air capture may be a great idea, but it is not going to give you the volumes of carbon dioxide that you want to start reducing compared to an actual capture process. You have a transportation, which you don't see here, which is typically pipeline, truck, shipped, depending on where you're located, but mostly pipeline. And then the underground storage using rocks as your storage container, or your storage complex, if you will. None of the technology or the approach to how this value chain is conducted is new. A lot of it comes from the oil and gas world. A lot of it also comes from transporting via pipeline or construction, engineering, construction, chemical engineering, refining, all these sorts of things. What is unique about carbon capture and storage, or carbon capture utilization and storage, is that it is stringing together existing technologies to solve a new problem in a different way. Instead of, in the oil and gas world, extracting something, you are instead looking for a way that you can inject or store carbon dioxide. Basically, in terms of regular capture, there's two different ways to do it. You can do it chemically using amines, or you can do it physically using membranes. And by far and away, the most expensive part of carbon capture, utilization, and storage, and if you want to throw transportation in there, throw that in there as well, is capture. This is just a figure I like to think of, to think about all the different ways that we could use, or we are trying to use carbon dioxide. So we can think of it as a useful product or as a waste product, depending on your approach. And this is a space where humans and our ingenuity and our ability to figure out ways to use things is an area for continued growth. So the more things we can find to do with carbon dioxide, the less of this, the less we would need to store. So the way that this works, the way that carbon capture and storage works, is essentially the Earth acts as a storage container. So this is what we geologists call a photomicrograph, which is a slice of rock looked at through a microscope. And the blue that you see is actually coloring on the slide, which represents open space in the subsurface. So if you think about sand, or from a macroscopic perspective, a crate of oranges where all of those oranges touch each other, the space in between is this, which in the subsurface, 2,000 meters, 1,000 meters below our feet, is filled. It has either very, very salty water, 6-7 times saltier than the ocean, oil, gas, but these pore spaces are not empty. And so when you are storing carbon dioxide, what you're doing is compressing it and dehydrating it, and then storing it in these pore spaces with that super salty brine. And so I would call this a rock formation like this in the subsurface a saline reservoir. But it's not a big open space. So when we think reservoir, maybe you think like a pool, but it's not a pool, it's these little spaces. So the questions typically that geologists and reservoir engineers ask themselves are three things. Can you inject something into the subsurface? And at what volumes can you do that? And at what pressures can you do that? Capacity, how much can an area hold? And containment, can you keep it in the subsurface once you put it there? And so the projects in Illinois, there are two of them. They were really pioneers and did everything, especially related to bioenergy, carbon capture and storage, for the first time. The first permits. There's two different projects. I'll show you a better photograph of that. The first project stored 1 million tons. The second project is still storing, and it has about 4 million tons stored in the subsurface. All of the monitoring and characterization and background work that needs to happen was done in these projects. So here's Chicago. This outline on this map is a geologic feature that is under the states of Illinois, Indiana, and Kentucky. It's about 60,000 square miles and very deep in places. So apologies for the Rio de Janeiro analogy here, but we weren't fast enough to think about that. But here's Christ the Redeemer. From top to bottom, this is about 800 meters. So if you think about, you compare that to the rock, here's the surface in Illinois, and here is the very bottom of that basin. It's about 3 of the top to bottom of Christ the Redeemer. The sandstone where we're storing carbon dioxide is about 17 or 1,800 meters beneath the surface, and it's about 500 meters thick. Sitting directly on top of that is a different rock type, which is impermeable, so nothing passes through it, which is called the Eau Claire Shale, and it is about 150 meters thick. Oil and gas is here at about 1,100 meters beneath the surface. And in this area where people get their water for drinking or for industrial purposes is at the surface. So the important part is that the storage of carbon dioxide is happening very far, very deep beneath surface activities. And you are permanently storing that carbon dioxide. This is what it looks like on the surface, just to give you an idea. This is the first injection well, this is the second injection well, and deep monitoring wells. The carbon dioxide is being captured here, the blue or the purple box, and at about the amount that the ethanol production facility creates is 3,000 tons of carbon dioxide per day. So the majority of that is being captured and stored at this location. And then you may be able to see it, there's a small line here, which is a pipeline that goes from the compression dehydration facility to the wellhead. So when I think about this in terms of oil and gas, if you think about the oil and gas terminology, we go from upstream to midstream to downstream, exploration, processing, and transportation to finished products. So there's also a CCS value chain or a carbon capture and storage value chain, but even though it's moving in the same direction, the activities are moving in the other direction. So you're starting with a finished product, which is carbon dioxide. You're transporting it, so the midstream is a bit the same. You're transporting or you're using it to enhance your ability to produce hydrocarbons or oil and gas. But the storage piece is more like exploration because you are, again, using that suite of technologies to solve a different problem. I'm going to go through these particular slides sort of quickly because this is just to show you all the different kinds of things you need to do to understand the subsurface to get a picture. So you drill wells, you take core samples, you run logs, you do a lot of what I would call characterization or screening to understand whether or not the rocks that you are going to store in are suitable for that storage. That is that package we're looking for, a place to store and a seal to keep it in place. This is actual rock from the project and this drill rig. So this always happens in drilling. So the beautiful photograph, right? Very early in the morning is February, which in the United States means it was like 10 degrees below zero. So like very cold, very beautiful, but very cold. And then in this rock is similar to that photomicrograph that I showed, the porosity and the permeability, the connectedness of those pore spaces, very important for us to understand storing CO2. You also use seismic reflection or seismic analysis, which I think about in my very simplest terms. If anybody has children or has siblings or something, it's like a sonogram of the earth. So you are sending sound down and measuring the reflections in order to be able to create a picture of what is happening in the subsurface. You want to know if there are faults or pathways that carbon dioxide could move. And so you also use this information to start to build models so that you can show the regulator, we understand the storage container, and we know we will use that information to monitor before, during, and after in the way that we will ensure that the carbon dioxide that you're putting in rocks is staying there. And so that process of understanding the rocks and the potential for storage and containment becomes the basis for your monitoring system, which becomes the basis for your risk mitigation. And so you are literally understanding and exploring the risks associated with all of these activities as you go, and then you're designing, engineering your systems so that you can monitor or reduce the potential for risk. I'm gonna skip that. This is just shows the wide variety of monitoring technologies that we tested and deployed. The difference between this very dense square and this square up above is the first project was a research project where we tried every possible monitoring technology. The second project, more commercial, and the one that's still operating, we were able to decide which of the monitoring technologies really gave us the most information and was the most useful. So then you start to also take into consideration cost, operation, what do you really need, information do you really need to be able to provide to the regulator, instead of, woohoo, we can do, let's test everything, which is where we started. You use a lot of simulation modeling in conjunction with the understanding of the subsurface. Where are the different plumes. This is the CO2 from the first project and the CO2 from the second project. You also use it to understand this information to understand and backwards model or history match the reservoir response to the stored CO2. So this is actual data, and then you match that with you adjust your model so that you can improve the quality of the model that you have. One of the most interesting science parts of the work that we did is that there were micro seismic magnitude response to the reservoir. So we had very, very strong sensors in some of the wells, which allowed us basically to listen to the rock as we were injecting carbon dioxide. So one of the questions I often get when I'm talking to people is, will your activities, your storage activities, cause an earthquake? So an earthquake, by definition, is a felt seismic event, like you can feel something. That happens at a magnitude of about 2.5, which magnitude is an exponential scale. So these events happening in the subsurface, a couple of kilometers in the subsurface, on the order of -1 or 0 magnitude. So you can't feel them, but we were able to detect them and know that they were happening. So this is an important finding because in the first project, we were injecting at a location that made these microseismic events possible. We mitigated this potential risk, if you will, by, in the second project, injecting the carbon dioxide about 50 or 75 meters higher in the rock, which then resulted in there being no more of this, these microseismic, essentially no more of these microseismic events. So a big learning. And the reason why is it relates to the subsurface geology. And yeah, so, but let me, in sort of as I start to wind down on this presentation, talk about all the other stuff, because this is where it actually, in my humble opinion, gets more complicated. The technology is actually pretty straightforward. But where does the money come from? Do you have a carbon market? What is the business model? Where do you put pipelines? What is your goal? Is it to reduce emissions or is it something else? Like all of that is it changes a lot and it depends on who you're talking to. And a lot of these pieces need to be in place before you can actually deploy the technology at large scale. In the United States, we have an existing regulatory framework, policy incentives. We have a tax credit, for example. We've done a lot of research to reduce uncertainty and mitigate risk, as I was just talking about. There's a lot of government support, or there was. There's big efforts, especially in the capture area, research area, demonstration to reduce costs. The more projects you do, the more possibility you have to reduce costs. And industry is starting to take over and do the work that the government supported, sort of got off the ground in the early days. I don't want to describe this in detail, but in the United States, the regulations are designed to protect underground sources of drinking water. So it's very specific where the environmental protection is directed. So everything you do needs to demonstrate that you will not harm a current or future source of underground drinking water, which is has a very specific concentration of total dissolved solids and a volume of production. So can you get water out of an aquifer, and what is the chemical composition of that water is how an underground source of drinking water is defined. This just gives you a sense of how many permits are being applied for in the United States, and a little bit about the tax credit. These are details we don't need to go into. But one thing that is interesting when you look at the trajectory of the tax credit and the changes and the policies from 2020 to 2023 and to 2025, there were some important changes in the tax credit, which allowed for the dots are proposed or actual projects. The size relates to the volume, and the color relates to the source of carbon dioxide. And so you can see in 2020 there were some important changes there was an increase in the value of the tax credit, and there was something that allowed you to transfer who owned or who got the benefit from the tax credit. Once that happened in 2020, you see a huge number of a big increase in the number and size of projects. And then that continues pretty much to this day. That also in this time period was a lot of federal funding that came out of the COVID pandemic, an investment by the federal government, by the Congress, to do additional clean energy work in this space. So there was also a lot of research money that got added into the incentive, to the efforts. So a few other things. One is that, you are all going to be professionals in this space or some other space going forward. And one of the things that I found the most interesting in the 25, 30 years that I've been doing this is that the questions that I get asked by the public are the same questions that we are asking ourselves as researchers, as engineers, as people who are tasked with making real the political aspirations. So somebody can say in 2030 we want net zero carbon dioxide, and everybody in this room has to figure out how to make that happen, right? And we ask ourselves research and engineering questions. What's the process? What's the, how are we going to do that? And so it's super important to realize that when somebody in the public is trying to understand what you're doing, they're going to ask you questions that are using different language, but are essentially asking the same thing. So a good one is, how do you know that carbon dioxide is staying where you put it? Well, I had 6 slides on monitoring technologies, and there's a whole, side or a piece of this industry that's all about you being able to answer the question, how do we know that the carbon dioxide is in the subsurface, and how can I prove it to the regulator, right? And so, or a question about earthquakes. We had a whole conversation now about microseismicity and is it going to cause earthquake? So learning to listen to what people are actually asking, because maybe they don't always have the words to ask the question in the same way, and tying it to what you know that you are already doing is a way to make connections for people to say, you know what, that's a great question. That's exactly why we're doing this research or this project or this pilot study. The other thing is that, I had that slide at the sort of in the beginning where I talked about barriers and obstacles and challenges. So, when you have an onion and you peel a layer off of the onion, right? Then there's another layer and another layer, or like those Russian nesting doll kind of things. So the thing with carbon capture and storage is each time you peel a layer off the onion, there's another layer. And so the challenges and the questions and the approaches have not really changed in the last 30 years, but what has changed is the depth of our understanding, the complexity of the problem that you're trying to solve, and in some cases, it's gotten a little bit harder as more and more people are familiar or understanding that these activities are taking place at all. So the message here is that you have to have some fortitude, some strength, because it is maybe not an easy path, but it is a very rewarding one. And the longer you stay in this work, the more questions that get answered, but the more questions that come up. And so you always have to be thinking about that. As I just said, carbon capture and storage is not an easy solution, but it is a necessary solution in terms of reducing how much greenhouse gas we're emitting. I believe we need to work smarter, harder, and faster to advance this work beyond business as usual. So it isn't exactly, even though it's similar, uses the same technologies as oil and gas, it is not exactly oil and gas. It's a new industry, and we have to recognize that there's still going to be several onions in our basket that need to be peeled and addressed. This kind of work requires an all of the above. We need all of the energy sources that we have available to us. We need all of the environmental solutions that we can. The way I think about it, in the United States, we're very focused on what is our retirement portfolio, like how much investment do I have in one area or another. You need a balanced investment portfolio. You need stocks, you need bonds, you need cash under the mattress, you need a gold bar or two, and you need all of those things. Like, you just don't want one, right? You want a mixture. We need policies, and we know that policies impact the ability to drive these activities forward. In Brazil, there's a lot of conversation about what kind of carbon market, are you going to have a carbon market? Like, what drives the ability to do, what pays for our desire to have net zero? And then leveraging or building off of the work that has already been done. So as I said earlier, Brazil does not have to start where the United States or the UK started 25 years ago. You can leverage that experience and learn in the international knowledge sharing space from others who have paved the way before you. What I think we need infrastructure, we need people in the workforce who are skilled. One of the things that I think is a huge advantage in Brazil is that you already have people who are process engineers, who are geophysicists, who are geochemists, who understand and have the possibility to work, have already had the possibility to work in this space. We need alignment, or to have shared goals and shared understanding of where we want to be. There's a lot of questions still to be answered. Ability to keep peeling the onion. You also need trust. You need to build relationships between industry and the regulator, between the operator and the neighborhood or the location where you're storing. I think we need a sense of stewardship, of responsibility for the earth and for our commercial activities. Fortitude, as I said, strength. You need to be, willing, and a little bit of an explorer or a pioneer. All of those things, and part of why it's such a delight to be here talking to all of you is that we also need to be passing knowledge across generations. That's to keep me on time. And so the way that I was raised and trained to think is not necessarily the way that current people who are being educated, who are doing PhDs, who are doing master's degrees. You have a different world than the world that I came from. So like understanding how those generational components influence where we go with technology and the problems that we solve is also super important to recognize and to be aware of. Some final thoughts. As I mentioned, we know that you can safely store carbon dioxide and protect human health and the environment. The technology is in place, as I believe I said at the very first. Geology is always going to be a critical factor because you can have many places where you can capture carbon dioxide and pipelines that you need to transport that carbon dioxide, but you're only going to be able to store it in certain places. And baseline, understanding the environment before you start to store carbon dioxide, tracking that while you're storing it, and after you've finished injecting, all of that is how you monitor and ensure safety. Simplicity is a critical factor. Some of the research wells that we drilled, for example, very, very complicated. And they had mechanical issues. And so knowing the art of designing systems that are effective, but also simple and not overly complicated so that you can ensure that they continue to perform over time. And then the additional societal pieces that we talked about that are super important. Regulatory framework, that is being decided, written right now in Brazil, which is really exciting and very interesting. The policy framework, science and engineering do not work at the same pace as politics. In the United States, we get a new president every 4 years, or sometimes every 8 years, depending, right? But science takes 30 years. And so those two things do not match. And being able to, make sure that we have sort of an evenness to our ability to do this work over political changes is super, super important. There needs to be a financial mechanism, whether that's a tax credit or a market, and then people have to want or at least be neutral to the activities associated with the overall goal of reducing greenhouse gas emissions, thinking all the way back to the second slide in this presentation, because we have global climate and weather issues that are impacting society. With that, I thank you very much. I'm happy to answer any questions. Yeah.
I have one comment and one question. Comment is, throughout your presentation, I'm very interested in seeing life cycle analysis of this because it seems to require a lot of energy. And where is this energy coming from? I don't know if you have comments about this, but I'm very interested in looking at them. And then my question is, you mentioned in the very beginning and the end about that we could start from the middle of something and not from the beginning, because there's work that have been developed. How do you see that it would be a suitable model for technology transfers between our countries, for example? Would it be an initiative from governments, universities, or individuals?
Okay, so for the purposes of the recording, maybe if you didn't hear that, I don't know how good the microphone is, but you asked about life cycle analysis, and you asked about how do we go about the technology transfer and accelerating Brazil's ability to learn and leverage from others. So I am not a life cycle analysis expert. Many people have looked at life cycle analysis and conducted studies that look at, for example, parasitic or how much energy do you use in order to be able to store carbon dioxide? What is the actual carbon intensity or carbon footprint? Always with life cycle analysis depends on where you draw the box, where do you start, where do you end, but there's a lot of literature and work that's been done in that space. With respect to information, knowledge transfer, you mentioned governments, universities, individuals, industry, all of those things, all of those locations, I think are opportunities for knowledge sharing to take place. Me standing here talking to you today is a perfect example of that. But doing a study abroad and having the opportunity to work at a project that is underway, or Fulbright scholarships or opportunities, working in a company here like Petrobras or another oil and gas company or an ethanol producer, something where you are doing an internship and you have the opportunity to interact in the international space. Publishing papers, going to conferences, all of those things really provide the basis and the opportunity for us to share knowledge and to learn from each other. And one thing I will say about the carbon capture, utilization, and storage space is that it has been a goal since the very beginning to be open and to share as much information across different countries. There are memorandums of understanding between different countries like the United States and Brazil, or the United States and Norway. So those sorts of pathways for knowledge sharing are very strong.
Yes, good morning. Thanks again for your presentation. My question will be about the implementation of the Mikado project in Illinois. Have you faced any resistance from the neighborhood, given that it's a new technology? Talking about CCS, it's a new technology. The neighborhood was not concerned about that technology, given the amount of risk associated. It's not very known. You mentioned about earthquakes, but there are also a risk of CO2 leakage. So how was the relationship with the neighborhood prior to the implementation of the project?
So that's a great question. Thinking about what is the public response or the public interaction. And one thing to understand about this particular area is that it is not near large city, so it's very rural and very agricultural focused. In this region of the United States, we grow a lot of corn and soybeans. So, and what you have here is an industrial complex that is owned and operated by Archer Daniels Midland, which is a food chemical processing company. They deal with starches, they deal with oilseed, they make ethanol. So the community or the citizens in and around the city of Decatur, many of them work for this company and are familiar with the activities of Archer Daniels Midland being essentially a large part of the economic driver of that particular location. The thing about interacting with society is that all the things that I just said are specific to a location. So what is the environment? What is what drives the economy? Do people work at the plant? Do you have historical issues that might be of concern? So all of that is homework that you need to do before you start to build a project or work on a project. And that also becomes part of understanding what risks are associated, what risks might be of concern. So that is a really long way of trying to answer your question, because in the early days, like this work started in 2000, and we started planning this first project in 2005, and the injection activities took place between 2011 and 2014. So the conversation with the public or with the people in the neighborhood was very different then than it is now. And a big part of what has changed, and it was very easy to say, you know, we're going to do this project, it's a research project, these are the things that we're hoping to learn, and so we had very positive interaction with the neighborhood and the citizens and the people who worked for Archer Daniels Midland. What is different now is that as more and more knowledge of carbon capture and storage, as we started to talk about larger volumes, as we have started to build the infrastructure, more people have become aware and have more questions. So I believe that when we started to talk about big, and by big I mean long, pipelines that go across a third or 2/3 of the United States, is when it started to really become part of the public mindset, and that has made public interaction more challenging. Not insurmountable, but more challenging. And more important. Yeah.
Great, thanks. My concern is about the environmental impact. So have you started with any negative impact related to leakage, for example, in those projects?
Yeah, so just to repeat that, a concern about the potential for environmental impact, and did we study that, and have we noticed any environmental impacts? So the monitoring system, which is in place, has monitored for 7 years before we started injection, has monitored in the, collectively in the 11 years that injection has been happening on location and continues to this day. We've seen no, what I would call out of bounds conditions. So nothing at the surface that indicates that you have CO2 anywhere other than the deep subsurface. There was an incident, a fluid migration incident through this monitoring well and this monitoring well last year, which resulted in an action by the regulator that required additional assessment and research, because there was brine, that salty water, and carbon dioxide that moved through the inside of the well, not as a result of the geology, but from one location in the well to another. And the carbon dioxide, which was the permit, has a very specific depth at which that carbon dioxide can reside, and which is from about 1,800 meters to 2,500 meters beneath the surface. They had carbon dioxide at 1,600 meters. And so while it's nowhere near the surface, it was in violation of the conditions of the permit. Some people might think, oh, that is a failure. That shows that this doesn't work. What I think it really means is that the monitoring system did exactly what it is designed to do, which is to tell you that you have carbon dioxide in a place where you are not permitted to have it. You go in, you assess the potential impact, you remediate, and the regulator is doing their job and the operator is doing their job. So it, to me, is a test of the quality and the robustness of the monitoring system in order to protect the environment. So, but you're always looking for, do you have carbon dioxide in a place where you do not expect it? The challenge with carbon dioxide is it's everywhere. It's in the brine, in the salt water, it's in the, part of the mineral makeup of the rocks, it's in the soil, it's in shallow groundwater, it's in the atmosphere. So you need to understand the fingerprint of the, or the signature of the natural environment, the pre-environment, the current environment, and the post-environment. And that's where the environmental monitoring is a key component of my ability to answer that question. You're welcome. Yeah.
Thank you for your presentation. I have some technical questions. Did you guys have any problems about the injectivity loss because of salt precipitation near the well?
You said injectivity loss?
Yes.
Yeah, okay.
Because of salt precipitation and times migration? How do you guys handle it?
Yeah, we did not have any significant injectivity loss. There was a situation where there was some pump oil from some of the infrastructure that was needed to be mitigated and remediated, which had some impacts, but nothing of any significance.
So at no point you guys have problems about injectivity loss? And
No. All right, well, thank you. Oh, one more, yeah?
And mine is more specific because I was researching this flow force medium for CO2 capture, and at that time we used models that use the solid nature has studied. And I want to know if there's still a problem with the reactive geochemical matrix, like dynamic transport properties, and it's a problem, and models to solve this problem.
I do not know the answer to that.
Yeah, the solid matrix for the model that we were using, we studied like the geochemical solid matrix,
Yeah.
static. And I was reading that the problem is that there are reactions in the geological matrix with the CO2 and the acids and the saline property of the solid, and this changes the porosity and the permeability. So
Yeah,
this is important, or
well, it's important to understand because what makes water salty, I think everybody in this room probably knows this, are cations and anions, right? So when you store carbon dioxide, what happens geologically is that the water and the concentration of carbon dioxide or chlorine, iodine, all of your anions and your cations, there's a buffering or a natural process where the water always wants to be at a neutral, at its base level pH, if you will, right? So you have calcium cations that combine with HCO3 2 minus, right? And you form a mineral. But that, and that mineral maybe drops out. But the kinetics of that are actually quite slow, and the environment is dynamic because the concentration is always changing. So in order to understand that, and to your point, really, when you think about injectivity, you need to be able to model what those conditions are.
then a reactive model.
Yeah, do you want to say something?
The timeline is.
But it's really long. The kinetics are, thousands of years, tens of thousands of years. So,
Can I take
yeah, of course.
I've worked CCF from an industry standpoint, from ExxonMobil standpoint, and the comment I've made is that those questions are more thought about for academic reasons and not practical reasons, because it will take hundreds of thousands of years for those kinetics, for those solids to drop out.
But
And
like
affects the
from old well, for example, from old well, like leakage problem.
Not in terms of the reactivity necessarily, with the reservoir. But the probability of having corrosion in a well, and that being an issue with CO2 getting to the well and escaping is much larger than the reactive
Then the geology.
geology.
Yeah, so it's
Yeah,
the
so-
human construction that is your most vulnerable. The geology has held oil and gas for hundreds of millions of years. So your ability to really alter the earth is limited, whereas Alana just said, your possibility of creating corrosion or some sort of impact to the human infrastructure is much more likely.
And even for wells that are existing, what we call legacy wells, in projects where we want to inject CO2, the main issue with the legacy wells is not even just the corrosion, but not knowing how those wells were plugged and abandoned. In the past, in the 50s, you would get these like piles of wood and throw inside the well to abandon the well, which is not how things are done today. And that would obviously not block the well. So if CO2 hits the well, you could have the potential to escape. So to the point you brought up earlier on safety, when companies are thinking about CCS projects, we stay very far away from places that have legacy wells or legacy wells that we don't have data on how they were P&A'd. But I think the reactive transport is something that academia studies a lot to understand it. It can be important in a specific type of formation called basalt, but for the majority of CCS that is being considered, it is going to matter in about 1 million years, 10 million years. So it's not that important. Thank you.
Okay, so let us thank again Sally, it was like outstanding. And guys, please help yourself, there's a lot of food, okay, so thanks. Obrigado. Pessoal, pode invadir mesmo. Sally's everything okay?
Yeah,
So maybe,
I have all my things.
let me see if I need to start.
Também tem uma